So now that we're comfortable with Boyle's law, Charles' law, Hamilton's law, and Avogadro's law, let's go ahead and combine these. In this module, we're going to look at our combined gas law, where we do just that. We combine the individualized gas laws we have. You do need to know how to use this equation. We're also going to look at your ideal gas law, PV equals nRT. So both these equations are fair game and you are responsible for them. Given the density of a gas at a certain temperature and pressure, determine the molar mass and vice versa. Yet another equation that you guys are responsible to know and be able to use. Know that your molar volume of an ideal gas is 22.4 liters at STP. That is a review from the previous module. And be able to solve stoichiometry problems involving gases. We've already done a few. Let's continue. So the ideal gas law. First, the ideal gas law is PV equals nRT. P stands for pressure, and in the ideal gas law, it depends on which gas constant unit you're using. We'll talk about the gas constant in a sec, but your gas constant here has specific units. This is the one that I use most often, so I will usually convert my units to get to this point. You are welcome to use any gas constant you need. You will get to the same point, but you need to put your final units in an answer that I want them in. Okay, so the way I'm going to teach you is to convert so that you always get to these units. Pressure in atmospheres, volume in liters, N is your number of moles, mole is your unit there, and T, temperature in Kelvin. We do have multiple versions of the ideal gas law. We do have multiple versions of the gas constant. For gases, when we're doing this kind of ideal gas law calculations and such, when we're talking about like volume, pressure, temperature, that kind of thing, we're going to use 0.0826 liter atmosphere per mole K. You have seen other units, but again, they get you the same point. We've already used like 8.314 times, or 8.314 joules per mole K. That's for energy. This is for when we're looking at gases specifically. Not gases in an energetic form, but gases when we're trying to figure out their volume or their pressure, etc. So first we have your combined gas law. You are responsible for this equation. Okay, so please learn this equation. There are three special cases. At constant temperature and constant volume, or constant temperature and constant number of moles, you have Boyle's law. At constant pressure and number of moles, you have Charles's law. And at constant temperature and pressure, you have Avogadro's law. I'll be honest, I know all the individual gas laws, but I tend to just start with the combined gas law, and then if something is constant, I just kind of cut it out from there. I'll show you what I mean in a sec. So what I mean by that is looking at this, looking at this overall equation, okay? If I have Boyle's law, what I'm thinking about is I do know Boyle's law, so I will write that out, but I know students have a hard time memorizing all the equations. So the kind of trick to this one is if you can remember your combined gas law, if you're under Boyle's law, you've got constant temperature and constant number of moles, which means temperature stays constant, number of moles stays constant. I get P1V1 equals P2V2, which equals Boyle's law. For Charles's law, same kind of concept. Write down your combined gas law. And at constant pressure and number of moles, I get V1 over T1 equals V2 over T2. Now, you do have to remember the specifics about that law to be able to do this. I understand that. Like, I know Boyle's law deals with volume being inversely proportional to pressure. I know Charles's law tells me that volume is directly proportional to temperature, which is why I'm able to do this. I'm not saying it's going to be the greatest help in the world, but it's one way to try to do it without memorizing all the equations. P1V1 over N1T1, P2V2 over N2T2. And here, it's constant temperature and pressure. So I get V1 over N1 equals V2 over N2. And Avogadro's law tells me that volume is proportional to the number of moles. Let's go ahead and work some examples so you can see how this works. A sample of gas has a volume of 2.8 liters at some unknown temperature. When the sample is submerged in ice water at 0 degrees C, its volume decreases to 2.57 liters. What is the initial temperature of the gas in Celsius? You can do one of two things here. You can start off and just recognize that you're dealing with volume and temperature, which means Charles's law. And you can write out Charles's law. V1 over T1 equals V2 over T2. If you're not great at remembering all the laws, you could also write out your your combined gas law, P1V1 over N1T1 equals P2V2 over N2T2. And recognize that it's only talking to you about volume and temperature, so you're going to cross out pressure and number of moles. It's going to get you the same equation. Here, it tells me I have an unknown temperature, but I'm given an initial volume, a second temperature, and a final volume. So I'm going to solve for T1. If I rearrange this equation for T1, I'm going to get T1 equal to V1 times T2 over V2. V1 is 2.80 liters. T2 is 0 degrees C, but I need this in Kelvin. For Charles's law, we have to be under absolute temperature. So 273.15 K divided by V2, 2.57 liters. This gives me an answer of 297 K, which I convert to Celsius by subtracting 273.15, which tells me my final answer is 24 degrees C. So if I have a volume of a gas at 2.80 liters and I submerge it in ice and cool it to 0 degrees C, the volume decreases to 2.57 liters. That means my initial temperature was 24 degrees C. Second example, I have a cylinder with a movable piston and a volume of 7.25 liters at 4.52 atmospheres. I want to know the volume at 1.21 atmospheres. Now again, if you recognize the laws, it's easier because you can say, okay, P1V1 equals P2V2. But sometimes you don't remember all the equations, and that's okay. That's where your ideal gas law comes into play and your combined gas law, P1V1 over N1T1, P2V2 over N2T2. And you cross out the pieces that don't matter. We've got pressure and volume here. So I'm going to cross out the pieces that don't fit. And it's going to give me the same equation. Let's see. We know our initial pressure is 4.52 atmospheres. We know our initial volume is 7.25 liters. We know our second pressure is 1.21 atmospheres. We want to know our second volume. So we're going to solve for V2. Rearrange our equation to solve for V2. P1 is 4.52 atmospheres. V1 is 7.25 liters. And P2 is 1.21 atmospheres. If you're ever unsure, just make sure your units are canceling. And we see we get 27.1 liters here. So, if I had a cylinder with a movable piston and had a volume of 7.25 liters at 4.52 atmospheres, the volume would increase to 27.1 liters if I decrease that pressure to 1.21. Notice 4.52 atmospheres, 1.21 atmospheres. I have decreased that pressure, so the volume has increased. Hence, Boyle's law. The other thing is some students have a hard time remembering this, and I understand that. So ideal gas law, we're going to use in the next equation, PV equals nRT. Okay? So our ideal gas law, what I want you to do on here is think about if you have your gas constant is this value here. This is a constant. It truly is a constant. So if I solve this equation for the constant, or rearrange this equation so that constant is by itself. If I have conditions under one reaction, and I have conditions under a second reaction, these R's are equal to each other. So what I can do is I can say, okay, I know these R's are equal to each other. Therefore, these equations are also equal to each other. I have now recreated my combined gas law by just knowing PV equals nRT. So by knowing one equation, I can recreate my combined gas law equation, and then I can recreate Boyle's law, Charles's law, Amontons law, Avogadro's law. What volume does 2.105 moles of ammonia gas occupy at 25 degrees C and 0.980 atmospheres? So I want to know volume. I've got 2.185 moles of ammonia gas. I don't really care what it is per se because it doesn't affect the properties of it other than, just knowing it's ammonia. But I want to know what volume it occupies if I have 2.105 moles of it at 25 degrees C and 0.980 atmospheres. For this, I'm going to use PV equals nRT. How do I know that? Because I'm not flipping between different pressures and volumes. I'm not using my combined gas law. I'm trying to find volume if I'm given moles, temperature, and pressure. So my pressure, 0.980 atmospheres. Volume's what I'm trying to solve for. Number of moles, 2.105 moles. My gas constant, 0.08206 liter atmosphere per mole K. And my temperature, 25.0 degrees C, which is 298.2 K. Why 0.2? Because I had a 0.0 here, so I need to add 273.15, which rounds up to 298.2. Rearrange your ideal gas law to solve for volume. So nRT over P, 2.105 moles times 0.08206 liter atmosphere per mole K times 298.2 Kelvin divided by 0.980 atmospheres. Make sure everything's canceling so you know you've got everything in the right units. Moles to moles, Kelvin to Kelvin, atmosphere, atmosphere. Notice this mole is in the numerator, denominator, numerator. This atmosphere is in the numerator, this is in the denominator, so I can cancel those out too. And it leaves me with liters, which is the units I want. I find my volume to be 52.6 liters. So if I had 2.105 moles of ammonia, this gas would occupy 25 degrees C and 0.908 atmosphere. It would occupy 52.6 liters for its overall volume. Okay, ideal gas law deviations. You need to know this equation. Some people do better with the deviation on how we get about here, how we get to here. So I'm going to show you the deviation. You are not responsible for the deviation, but again, some people do better with understanding the math behind it. If you don't, and you can just memorize this equation, great, do it. If you got a better mnemonic, that's awesome. The one I learned is from Dr. Fry, where she says density, and then she was raised in a military family, so she memorized it as military, police, MP, R, terrific. So military police are terrific. And since she told me that, I've never forgotten it. But let's go ahead and derive how we get there. So we know that molar mass is equal to your mass divided by your number of moles. I'm going to rearrange this equation, and I'm going to solve for number of moles. And I'm going to say mass over my molar mass. We also know your ideal gas law PV equals nRT. I'm going to substitute this in for N. So I've got PV equals mass over molar mass times RT. Now I'm going to rearrange this equation. Algebraically rearrange it where I've got your molar mass equal to mass divided by volume times RT over P. So what I did here, I took this and multiplied it by both sides. I took this and divided it by both sides. So 2 steps in 1. If you're not sure, come see me. But I need you to remember here, density is equal to your mass over your volume. Mass over volume. So your molar mass is equal to your density times your gas constant times your temperature divided by your pressure. You can also write this as density is equal to your molar mass times your pressure over your gas constant times your temperature. This is still mass over volume. So let's work a couple examples. A sample of gas has a mass of 3.11 grams and a volume of 2.25 mils at 55 degrees C and 866 milliliters of mercury. Calculate the molar mass of this gas. So note your volume does need to be in liters, 0.225 liters. Your temperature does need to be in Kelvin, so 328 K, and your pressure does need to be in atmospheres. So 866 millimeters of mercury, convert that to atmosphere. I know 1 atmosphere contains 760 millimeters of mercury, so 1.14 atmospheres. I want molar mass. Mass over volume times RT over P. This is just your density. Don't let it throw you off too much, okay? That is density. I've got 0.311 grams over a volume of 0.225 liters. Multiplied by my gas constant, 0.08206 liter atmosphere per mole K, times temperature, 328 K, divided by pressure, 1.14 atmosphere. Solve the cell out and we get 32.6 grams per mole. Calculate the density of a sample of chlorine gas, 25.04 degrees C and 759 millimeters of mercury. So I know density is equal to molar mass times pressure divided by my gas constant R times temperature. Chlorine gas is a diatomic, Cl2, so it will be 70.90 grams per mole for its molar mass. Temperature, 25.04 degrees C plus 273.15 to get to Kelvin equals 298.19 K. And pressure, 759.2 millimeters of mercury. This is almost 1 atmosphere, but not quite. I expect to be very close. 1 atmosphere is 760 millimeters of mercury. So this equals 0.9989 atmospheres. So I know my molar mass is 70.90 grams per mole. My pressure, 0.9989 atmospheres. My gas constant, 0.08206 liter atmosphere per mole K. And my temperature, 298.19 K. Make sure everything's canceling just to be safe. My kelvins have canceled. My moles have canceled. My atmospheres have canceled, and I've got grams per liter, which is what I expect for density. Calculate this out. Let's see, I get 2.894 grams per liter for my density. So the density of a sample of chlorine gas at 25.04 degrees C and 759.2 millimeters of mercury will be 2.894 grams per liter. Okay, just a couple more examples for this unit. A 3.50 gram sample of a diatomic gas in a 1.5 liter container has a pressure of 2.42 atmospheres at 355 K. Determine the identity of the gas. Molar mass is what's going to tell me the identity of a gas. So if you see identity, you're trying to solve for molar mass. There's a number of ways we can do this, and we'll do this throughout first and second semester of general chemistry. Remember the definition for molar mass? Sometimes, like in an equation with gas laws, it's easier to find it. Otherwise, remember, if you've got your grams, you can divide by moles, you've got molar mass. I know my density, which is my mass over my volume, times gas constant times pressure divided by pressure, or times temperature divided by pressure, is equal to my molar mass. So I've got a 3.50 gram sample in a 1.5 liter container, gas constant 0.08206 liter atmosphere per mole K, times my temperature, which is 355 K, divided by my pressure, which is 2.42 atmospheres. So my atmospheres have canceled, my Kelvin has canceled, my liters have canceled, and I'm getting grams per mole, which is what I expect for my units for molar mass. Calculate this out, and I'm going to get 28 grams per mole, but it tells me this is a diatomic, which means 28 grams per mole divided by 2, 14 grams per mole, matches to nitrogen. The answer here is N2. And for the last example for this module, the four most common gases in the atmosphere are N2, O2, argon, and CO2. Assuming all the gases are in containers of equal size, temperature, and pressure. Equal size means equal volume, temperature, and pressure. Which gas has the highest density? So let's think this through. So this means same volume, same temperature, same pressure. I know density is your mass over your volume. If all of these gases are under the same volume, pressure, and temperature, the sample with the highest mass will have the highest density. I have the same temperature, same pressure, same size, which means I have the same number of particles, but those particles weigh differently. So N2, 28.01 grams per mole, or O2, whichever way you want to round it. O2, about 32 grams per mole. Argon, 39.94 grams per mole. And CO2 is 44.01 grams per mole. So in this example, CO2 will have the highest density because density is your mass over your volume. They all have the same volume. They all have the same number of particles because they're under the same volume, same temperature, same pressure. But even though they have the same number of particles, a particle of CO2 weighs more than a particle of argon, a particle of O2, or a particle of nitrogen. So if I have the same number of moles of those, CO2 will lead to the highest density.